Prepping for a data science or AI interview? Well, you're definitely in the right place. Welcome to this explainer, where we're going to crack the absolute most common and, honestly, often the most tricky recruiter questions about large language models. Today, we're breaking down tokenization, embeddings, and out-of-vocabulary words. I'll be transforming these pretty complex algorithms into a clear, straightforward study guide. Stick around till the very end for the exact expert answers, the common candidate mistakes you need to avoid, and those pro tips that will seriously dazzle any technical recruiter. Let's get right into it.
Here's our agenda for today. We've got 1. The LLM tokenization pipeline. 2. Word versus subword tokenization. 3. Why embeddings matter most. 4. Capturing context and meaning. 5. Handling out-of-vocabulary words. And 6. A rapid-fire interview round. Mastering these concepts is really your secret weapon.
Section 1, the LLM tokenization pipeline. Let's dive right into how these models actually process text. Okay, so picture this. You're sitting across from the hiring manager, and they ask you, how exactly do large language models process raw text? It sounds basic, right? But a huge mistake candidates make here is jumping straight into talking about neural networks. When asked this, the recruiter really just wants to see if you understand the fundamental bottleneck, and that is, LLMs absolutely cannot read raw text directly. They only understand numbers.
To nail this question, hit them with his crisp, confident definition. Tokenization is simply the process of breaking text into smaller, manageable units, called tokens, so a language model can eventually process them numerically. You can think of it as the vital translation layer between human language and machine mathematics.
Then, to completely impress them, walk them through the exact 5-step pipeline. Notice the flow here. We start with the raw text, which gets chopped up into those tokens. Next, each token is mapped to a specific integer, becoming a token ID. Those IDs are then converted into dense mathematical vectors, which is what the neural network finally uses for its processing. Just mapping out this journey out loud already makes you stand out from the crowd.
Section 2. Word versus subword tokenization. Now let's explore exactly how we chop those words up.
This next one is a classic architectural trade-off question. The interviewer asks, why do modern LLMs prefer subword tokenization over word level? What they're looking for here is your ability to explain how we balance vocabulary size with flexibility.
So explain to them that word-level tokenization simply splits text by spaces. While that sounds super easy, it completely fails on unknown words and forces models to store millions and millions of full words. On the flip side, subword tokenization is the industry gold standard. It smartly balances model efficiency by keeping the vocabulary size manageable, while simultaneously giving the model this amazing adaptability to handle rare or completely unseen words perfectly.
To really drive it home, throw out a real-world example. Take the word unbelievable. A subword tokenizer splits that into 3 distinct fragments: un, believe, and able. By explaining that, you prove to the recruiter that you actually know how these algorithms are operating under the hood. Section 3. Why embeddings matter most. Now, this topic is what truly separates the beginners from the AI experts.
Seriously, if you only remember one single thing from this entire explainer to take into your interview, let it be the answer to this exact question. What is the key difference between token IDs and embeddings? A ton of candidates get these two confused, and trust me, it is a huge red flag for recruiters.
So here is the crucial distinction you need to make. Tell the recruiter that while token IDs are just arbitrary integers used for lookup, embeddings are the dense, high-dimensional numerical vectors that capture the actual semantic meaning of those tokens. Token IDs have zero real meaning. They're literally just a dictionary index. Embeddings are where the magic actually happens. They capture the word soul.
Think about the words cat and dog. Their arbitrary token IDs might be something like 1052 and 3481. Completely different, totally unrelated numbers, right? But consider their embedding vectors. They are numerically incredibly close in vector space, maybe something like 0.21 and 0.19. Why? Because the model knows their semantic meanings are highly similar. Explaining that distance in vector space literally equals similarity in meaning will score you massive points.
Section 4. Capturing context and meaning. Let's see how these vectors get even smarter in modern models.
When an interviewer hits you with a tricky scenario question like, how does an LLM know which definition of the word bank to use? They are straight up testing your knowledge of modern transformer architectures. And they're eagerly waiting to hear you say one specific magic phrase.
And that magic phrase is contextual embeddings. You explain that in older models, a word just had one static vector, but in modern LLMs, embeddings are contextual. The transformer architecture refines embeddings layer by layer, so the exact same word bank gets assigned a totally different mathematical vector in the sentence deposited money in the bank compared to sat near the riverbank. It's dynamically reading the surrounding text.
Now, if you really want to seal the deal, drop this massive pro tip on them. Mention the famous AI equation, king minus man plus woman equals queen. Tell them that without embeddings, this is completely impossible because LLMs would only see arbitrary integers. But because embeddings encode deep human-like relationships into semantic vector spaces, we can literally do math with language. It's a fantastic flex of your foundational NLP knowledge.
Section 5. Handling out-of-vocabulary words. Let's transition to a highly technical, real-world scenario.
In the past, this was a massive headache for data scientists. The interviewer will ask, how do modern models handle out-of-vocabulary, or OOV words? A very common beginner mistake is just saying, oh, it outputs an unknown token. Actually, scratch that. Your confident answer here should be that true OOV problems are extremely rare nowadays, all thanks to our trusty friend, Subword Tokenization.
Give them a fun, modern example, like the made-up word ChatGPTization, a word that obviously wasn't in any older training data. Even if the model has never explicitly seen this brand new slang, it doesn't crash. It just easily breaks it down into known fragments, like chat, GPT, and isation. This allows the model to infer the meaning without failing. It's an absolutely brilliant system for handling the endless creativity of human language.
Section 6. Rapid-fire interview round. All right, let's wrap this up with a super high-energy rapid-fire round to prep you for those quick-hit trivia questions.
Definitely commit these key takeaways to memory. If they ask for subword algorithms, immediately cite BPE, which is byte pair encoding, and word piece. If they ask what types of embeddings exist, rattle off the 4 main ones: token, positional, sentence, and document. And finally, if they ask how models handle absolutely crazy, never-before-seen symbols like wild new emojis, always mention byte-level tokenization as the ultimate bulletproof fallback.
And that completely wraps up our interview prep explainer. You now have the smart, structured answers you need to handle tokenization, subwords, and semantic vector spaces like a total pro. But I'll leave you with this final, provocative thought to ponder. If embeddings perfectly capture the meaning of our words today, how will dynamic tokenization shape the next generation of AI models tomorrow? Let me know your thoughts in the comments. And hey, if you found this explainer helpful, please hit that like button, subscribe for more expert study guides, and comment below on which AI topic you want explained next. Good luck out there on your interviews.